All right, this video is on basic integration. It's a review from Calc 1, but we want to get real good at these because we'll move into integration techniques in a couple of videos. So the first thing I want to talk about is real quick a review of the difference between these two symbols. So if I'm looking at the integral of x squared dx versus the integral from 0 to 2 of x squared dx, both of those symbols look about the same. We talked about this in more detail at the end of the previous video, but the one on the left means to find all antiderivatives of x squared with respect to x. Okay, so with respect to x. The one on the right is the definite integral. It loosely means find the area under the graph x squared from 0 to 2. So the thing on the left, the answer is going to be a function or several functions. It's going to be all the antiderivatives of x squared with respect to x. The one on the right, the answer is going to be numeric. It's going to be area underneath a curve. Okay, so on the right, we determine any antiderivative. One such antiderivative is 1/3 x to the third, and we put 0 into it in the end, and then we plug in the 2, plug in the 0, and subtract. So we get 1/3 times 2 to the third minus 1/3 times 0 to the third, which then gets us 8/3. So the area under the graph x squared from 0 to 2 would be 8/3. The one on the right, we're looking for all of the antiderivatives of x squared. And so in this case, it would be smart to start with x to the third, because the derivative of x to the third is 3x squared. We put a 1/3 in front of that because now if you take the derivative of that, when you bring the 3 down, 1/3 times 3 is 1, and the derivative of 1/3 x to the third then is 1x squared. And so we have what we want. You can then add any constant you want. So for example, I could say instead of 1/3 x to the third, I want 1/3 x to the third plus 7. That would be an antiderivative of x squared because the derivative of 7 is 0. I could also do 1/3 x to the third plus 26. I could do 1/3 x to the third minus 5, because in all three of those cases the derivative of the constant is 0. In all cases the derivative of a constant is 0. And so the way we indicate that is we put plus c. Plus c indicates we can add any constant we want. So c could be 7 or c could be 26. It would take care of subtraction because c could be -5, and so we could express that as plus -5. That covers all antiderivatives of the function x squared with respect to x, and so that's the answer to the problem on the left. Again, as we discussed in the previous video, and as you probably discussed in Calc 1, the one on the left is called an indefinite integral. The one on the right is called a definite integral. We will focus on indefinite integrals because doing a definite integral simply means that you're going to do the antiderivative, you're going to do the indefinite integral, and then plug in the two values. When you do the definite integral on the right, typically we choose for c to be 0. C doesn't have to be 0 because it would subtract out. And again, if you go look at the previous video, you can see an example where we showed why those would cancel out. Okay, so I want to start talking about a lot of antiderivatives. And so we're going to do a ton of examples in this video where we just do things like the integral of x to the 8th dx, and then the integral of x to the 5th dx. And most of this should be review from Calc 1. We'll kind of advance fairly quickly, but real quick, we're trying to find all of the antiderivatives of x to the 8th with respect to x on that first problem. A good place to start there would be x to the 9th because because the derivative of x to the 9th is 9x to the 8th. We put 1/9 in front because now when we bring the 9 down, you get 1x to the 8th. Again, you add plus c because the derivative of any constant is 0. Doing the same thing on problem 2, we would start with x to the 6th. We put 1/6 in front. Now the derivative of that is 1x to the 5th, which is what we wanted, and then we put plus c. Okay, this pattern works for just about any power function. So a power function is when you have x to a number, so x to a power. X to the 8th works, x to the 5th works. If I have x to the negative 4th, x to the 2/3, x to the negative 7/5, and x to the negative 1. If you can, pause the video, try those 4 problems and simplify your answers, and then check them with me here in just a minute. So please pause the video and try the problems now. Okay, so we can actually do the same thing that we did on the first 2 problems. We could start with x to the negative 3, because the derivative of x to the negative 3 is negative 3x to the negative 4. We're going to put 1 over negative 3 in front and put a plus c. If we check that, you bring the negative 3 down, it cancels, and then you get x to the negative 4 as the derivative. To simplify this, you move the negative exponent to the bottom, and we can make it negative 1 over 3x to the 3rd plus c. That's the answer we should put for a problem like number 3. For number 4, we can follow the same pattern. Start with x to the 5/3. If we follow exactly what we've been doing, we would put 1 over 5/3 in front. You don't have to write it like that, and you definitely should not leave it like that, but now we're following exactly the pattern that we did on the first 4 problems. So it's you add 1 to the power, it's 1 over whatever that is, and then x to whatever that is. When you have 1 over 5/3, that's the same thing as 3/5, obviously. So we get 3/5 x to the 5/3 plus c. Okay, on number 5, negative 7/5 plus 1 is negative 2/5. We then get negative 1 over negative 2/5, x to the negative 2/5 plus c, which is negative 5/2 x to the negative 2/5 plus c, and then you can move the negative to the bottom, negative exponent to the bottom. So negative 5 over 2x to the 2/5 plus c, that's the best form of the answer. Okay, when we get to problem 6, if we follow the same pattern, we get 1 over 0 x to the 0 plus c. That obviously doesn't work because you can't divide by 0. So writing 1 over 0 x to the 0 doesn't actually mean anything. And so we have to think of something else for that. So I want to take a second before we do that problem and kind of write what we're talking about on the first 5 problems in a simple rule. So we've got what's called the power rule. And what the power rule says is that the antiderivative of x to the n dx, or the integral of x to the n dx, is 1 over n plus 1 x to the n plus 1 plus c, as long as n is not negative 1. Okay, so that's probably the most common antiderivative rule we'll use. We'll have a lot of them, but that's the one that comes up the most. When x is negative 1, so that's what we were doing on the first 5 problems. But when x is negative 1, that rule doesn't work. It's easier to think of that problem as 1 over x dx. So when I have x to the negative 1, it's obviously the same thing as 1 over x dx. And if you remember from Calc 1, we're trying to think of a function that you take the derivative of that would give you 1 over x as the answer. And so if you remember from Calc 1, the derivative of natural log x is 1 over x. And so there's a technicality where we have to put absolute value, but the derivative of natural log x is 1 over x, so the antiderivative of 1 over x ends up being natural log of the absolute value of x plus c. The absolute value has something to do with the domain. So when you talk about natural log, the argument, the thing inside the natural logarithm, cannot be negative, and it also cannot be 0. When you write x to the negative 1 or 1 over x like we did on problem 6, it's understood that x cannot be 0, which is good for log, but x could be negative. The absolute value kind of fixes that, if that makes sense. So the negatives become positive in that case. That's a rudimentary explanation, like a basic explanation of why that's true, but it is something we need to do when we're doing the log rule. If you want to talk more about why that's true, maybe we can do that during office hours or something like that. Okay, if there are any questions, just let me know. But let's write that rule. So the integral of x to the n dx is 1 over n plus 1 x to the n plus 1 plus c if n is not negative 1. If n is negative 1, we've got x to the negative 1 dx is the same thing as 1 over x dx. And the antiderivative of that is the natural log of x plus c. And so we'll use that rule quite a bit as well. Okay, and then I want to look at, so those two rules together cover all power functions. So power functions are when you have x raised to a power. The next type of function I want to look at is exponential functions. So power functions are x to a power. So x to a number. Exponential functions are when you have a number to the x. Okay, so obviously that's informal what I'm writing there, but power functions are x to a number, exponential functions are a number to the x. The one that we'll do the most often is e to the x dx. And so if we have e to the x dx, the antiderivative of that is e to the x plus c, and that's because the derivative of e to the x is e to the x. So I don't know if you remember from Calc 1, but when you do the derivatives of e to the x, it stays the same as long as it's just e to the x. If it's e to the 2x or e to the 3x or e to the x squared, it's more complicated than that. It's also more complicated than this if we're dealing with antiderivatives where the power is not just x. But for e to the x, the antiderivative is e to the x. That's the third rule that I want to add up here at the top. And so these three rules, we've got two for power functions. We've got the power rule, and then we've got the log rule, but the log rule is to deal with a power function. And then we've got an exponential rule for e to the x. We'll deal with other exponential functions later, so we can come up with a formula for other exponential functions. We won't list that as a basic formula in this class, but we can use U substitution, which is a topic we'll cover in 2 more videos in order to do ones where the base is not e. Okay, so at this point I want to look at a formula sheet. And so the formula sheet that you've got, this is in the shared folder under Unit 1, but this has the basic integration formula, so the basic antiderivatives. And if you look at the top, we've got the 3 rules that we just did. So we have the x to the n dx, we've got x to the negative 1 dx, which is the same as 1 over x dx, and then we've got e to the x dx. Those are the only 3 I want to get through on this video. I want to do some more complicated examples, but if you'll notice, we've got 6 more rules that involve trig. We've got 2 rules that involve inverse trig, and then we've got 2 additional properties at the bottom. The additional properties at the bottom say that the antiderivative of f of x plus g of x, man, there should be a dx on there. I'll have to fix the typo, but there should be a dx there, is equal to the antiderivative of f of x dx plus the antiderivative of g of x dx. And then that means basically you could split up addition. And so if you have several things added up in an integral, you can split it into several integrals. The second property, the constant multiple rule, says that if you have a constant k times f of x inside of an antiderivative, you can pull the constant out. Those correspond to basic derivative rules. So if you remember doing derivatives, when you have addition or subtraction, actually, you can do the derivative separately. When you have multiplication and division, you need a product rule or a quotient rule. And so addition and subtraction can be split up using or on antiderivatives. Constant multiplication, meaning a constant times a function, you can pull the constant out. These 2 rules, if k is negative 1, that would allow you to combine the 2 rules and actually get subtraction. But let's go look at some examples where we would do addition and subtraction and some things like that. And so some more complicated examples. Okay, so if I have on problem 8, the integral of, say, x to the 6th plus x to the 10th. dx. Most of us could do this antiderivative without splitting it up. It would be a good idea, you don't have to necessarily, but it's a good idea if you get in the habit of trying to make all of the integrals that you do look exactly like one of the 11 forms that were on the formula sheet that we were just talking about. So at this point, one of the 3 forms that we've got, either x to the n dx, or 1 over x dx, or e to the x dx. And so what I mean by that is we should not be getting rid of an antiderivative sign until we have the problems looking exactly like one of those 3. And so because of the addition property, we can split problem 8 into 2 separate problems where we have the integral of x to the 6th dx plus the integral of x to the 10th dx. Now both of those problems look like the power rule. And so the antiderivative of of x to the 6th dx is 1/7 x to the 7th. The antiderivative of x to the 10th is 1 over 11 x to the 11. And then we put just 1 plus c at the end, because if there was a constant with each of them, we could just combine them and make it one constant at the end. And so, like I said, I think most of us could do this problem without writing the middle step. But as problems get more complicated, it's going to be helpful if you get in the habit of writing it so that each antiderivative looks exactly like one of the 11 forms. So at this point, one of these 3 forms. Okay, so if I have addition, we can split it like that. If we have subtraction, we can actually do the same thing. If you have a constant multiple, so if I have 7x to the 5th, technically this doesn't match the forms because the 7 is not inside of an integral, or the 7 is not in any of the forms that we've got at the top of the screen. But because of the constant multiple rule on the formula sheet, we can pull the constant out, so we can pull the 7 out. We get then 7 times the antiderivative of x to the 5th dx. That gets us 7 times 1/6 x to the 6th plus c, which is then 7/6 x to the 6th plus c. And that's the answer here. Again, most of us could do this without writing those middle steps, but it would be a good idea to get in the habit of getting it to match the forms exactly. Okay, so let's look at a few more challenging problems. So let's say I have the antiderivative of 5x to the 3rd minus 7x squared plus 6x. And we'll go ahead and say plus 4 dx. Okay, when we do this problem, we're going to simultaneously apply the sum rule and the constant multiple rule. Those will let us split up the addition and subtraction into 4 problems, and we can pull constants out. So we're going to pull the 5 out and write the first problem as x to the 3rd dx. On the second problem, we're going to pull the negative 7 out and have x squared dx. So we've got 5 times the integral of x to the 3rd dx minus 7 times the integral of x squared dx. We're then going to have plus 6 times the integral of x dx. And then when we have a constant, we haven't talked about that, but you probably did in Calc 1. That's something where I'm not going to write a separate rule for that, but when we have a constant completely by itself, we're going to leave that inside, and we'll talk about how to do it in just a second. Now we've got 3 integrals, x to the 3rd dx, x to the 2nd dx, and then x dx, which is really x to the 1st dx. 3 integrals that match those forms exactly. One exception to that is when you have a number by itself. So if I have 4 dx, we're going to not, like I said, not going to write a form for that, but that's one where it won't look exactly like one of the forms, and we can still do the problem. When we do this, now we've got 5 times 1/4 x to the 4th minus 7 times 1/3 x to the 3rd plus 6 times 1/2 x squared. And so those 3 follow the rule exactly. You'll probably remember from Calc 1 that the antiderivative of 4 dx would be 4x. And the reason that's true is because the derivative of 4x is 4. And so then we put plus c at the end, and now we simplify. We get 5/4 x to the 4th minus 7/3 x to the 3rd plus 3x squared plus 4x plus c. And that's what we would write as our answer on problem 10. All right, I want to look at a few more quick examples before the end of this video. So number 11, let's say we have 5 over 4 x to the second. So when we're doing that problem, we're going to do two things simultaneously. First, we're going to pull the constant multiple 5/4 out. And then we're going to think of this as being 1 over x squared dx. But 1 over x squared does not match one of the forms. So if we look at the forms that we have on the formula sheet, or the forms that we wrote up above, we've got x to the n dx. We've got 1 over x dx. And we've got e to the x dx. So those are the three forms we have so far. This kind of looks like 1 over x dx, but that rule only works when it's 1 over x to the first, or when we do a u substitution later. But right now, it would be wrong to write natural log of the absolute value of x squared plus c. And I know that if we slow down and kind of think about that, we all know that that's not the case. And if you work the derivative of this out, it's 1 over x squared times 2x, which is why this is technically wrong. That's not equal to 1 over x squared. So if we slow down and think about it, we know that's not true. It's just easy when we're working on a ton of problems and we're working quickly to look at 1 over x squared and say, oh, well, that's in the form of log, so it's log of x squared. Be real careful not to do that. What you do instead is you rewrite 1 over x squared as x to the negative 2 dx. And now that matches the power rule. So if you have a fractional, if you have 1 over x to a power, we're going to rewrite that unless it's 1 over x to the first. Following the power rule, we then get 5 over 4 times 1 over negative 1, x to the negative 1 plus c. That gets us negative 5 over 4x plus c, and that's the answer. Okay, so if we have this problem, I would like you to pause the video and try this problem. So work this out slowly and then come back in a minute or two and then check it versus what I do. Okay, so we're going to split this into 4 separate problems, and we're going to pull the constant multiples out. So in the first problem, we're going to pull 3 over 7 out. That leaves 1 over x to the 4th inside, which we're going to rewrite as x to the negative 4 because it's not a negative 1 exponent. On the second part, we're going to pull the negative 5 halves out. That leaves x to the positive 2 inside because the x is on the top. On the third problem, we pull 1/6 out, and then we get x to the first, or just x, inside. And on the fourth problem, we pull the 3 out, so it's like 3 over 1, whereas the one before is 1 over 6. And then instead of writing it as x to the negative 1, we're going to go ahead and leave that as 1 over x because it's 1 over x to the first. If that had been 1 over x to the 4th, we would rewrite it as x to the negative 4th like we did on the first problem, or the first integral there. Okay, now we can do the antiderivative of each part. So we apply the power rule to the first one and get 1 over negative 3x to the negative 3. We apply the power rule again and get 1 over 3x to the 3. We get 1/2 x squared here, but on the fourth one we get natural log absolute value of x plus c. If you simplify these, you get negative 1 over 7x to the third. That, by canceling the 3's, you get then negative 5x to the third over 6 plus x squared over 12, or you could write it as 1/12 x squared like I have on some of the others, minus 3 natural log absolute value of x plus c. And that's the answer on this problem. Okay, so let's say we have 6 times the 4th root of x to the third minus square root of x over 5 plus 6 over the cube root of x. Okay, so if we have these, we can use properties of exponents to rewrite the radicals into forms that we can handle more easily. So when we do this problem, we split it into 3 problems. We pull the 6 out of the first one and rewrite that as x to the 3 over 4. So if we remember from algebra, the index of the radical becomes the denominator of the fractional power, and the power inside becomes the numerator of the fractional power. So the 3 is on top, 4 is on bottom. If that were in the bottom of a fraction, you would then rewrite it as x to the negative 3/4. On the second one, we pull negative 1/5 out, and we write it as x to the 1/2. So the square root, the index is understood to be a 2. The power on the x is a 1. So we get x to the 1/2 dx. On the third problem, we pull 6 out, and we get x to the negative 1/3 dx. Applying the power rule to these, we get 6 times 1 over 7/4 x to the 7/4 minus 1/5 times 1 over 3/2 x to the 3/2 plus 6 times 1 over 2/3 x to the 2/3 plus c. We get that by adding 1 to each of the fractions. Simplifying, we get 24 over 7 x to the 7/4 minus 2 over 15 x to the 3/2 plus 18 over 2, which is 9 x to the 2/3 plus c. Just kind of as a quick review, what I'm doing with those fractions is like 6 times 1 over 7/4. I'm making it 6 times 4 over 7, which is then 24 over 7. And so you may need to practice some of that, especially without a calculator, in order to get comfortable with the ones with fractions. Okay, I want to look at one more example on this video, and then I want you to try some problems before the next video. So if I have 5x squared minus 6x plus 7 over, say, 3x squared, we don't have a rule that will allow us to split up division, but what we can do when we have a single term in the denominator is we can split this into 5x squared over 3x squared minus 6x over 3x squared plus 7 over 3x squared. That then allows us to split this into 3 separate problems. And so we get, the integral of 5/3 on the first one. So because the x's cancel completely, I'm going to leave the 5/3 inside. We can pull 6 over 3, which is 2, out of the middle problem. But we get x to the negative 1, which is the same as 1 over x on the middle problem. And then we pull 7/3 out of the third one. And because it's left with x to the negative 2, we don't, or because we're left with 1 over x squared, we don't want to leave that as a fraction. We want to write it as x to the negative 2. Okay, so again, when you get x to the negative 1, inside the integral, you want to have 1 over x. When you have x to another negative power, you probably should write it as x to the negative power. The antiderivative of 5/3 is 5/3 x. The antiderivative of 1 over x is natural log absolute value of x. And the antiderivative of x to the negative 2 is 1 over negative 1 x to the negative 1 plus c. We simplify that and we get 5/3 x minus 2 natural log absolute value of x minus 7 over 3x plus c. And then it's important to notice that when you have x to the negative 1 in the problem, that's when you end up with natural log of absolute value of x. When you have x to the negative 1 in the answer, you do not end up with natural log in the answer. Okay, that's it for this video. I'd like you to now work the practice problems that go with this video. So it's called problem set 1 under basic integration. you have the answers but not worked out solutions to those. So you should work those problems and make sure you're comfortable with this. This should be review from Calc 1. It's just we need to get very, very comfortable using these rules. The next video will have more review problems from Calc 1, but will involve trig and inverse trig. Okay, thanks for watching.